So today we're going to take a second look at the first derivative test. In the previous video, I sort of went through the 5 steps. I'm not going to go through that again. We'll do that in the examples. But in this video, I want to talk about what the purpose of the first derivative test is. So if you were doing the problems yesterday and you didn't quite get what you were doing, what the point was, the whole point of the first derivative test is twofold. One, it lets you find the relative maxes and mins. And two, sort of at the same time, it lets you find the intervals on which the function is increasing or decreasing. And what that sort of means is, imagine, if you will, that, you've got a function that does this, right? You should be able to tell just by looking at it that this function decreases here and then decreases again here. And we can tell that it increases more or less between here and here. So what the first derivative test is effectively telling you is it's saying, hey, this is the interval where it's decreasing, well, this and this. And this region inside here is the region where it's increasing, right? So when a problem talks about finding the open intervals where the function is increasing or decreasing, you're just finding the regions in which that's happening. And like I said, these things sort of happen at the same time. To be honest, if I remember my steps correctly from the previous video, finding the open intervals of increase and decrease, I think happens basically during step 4. Finding the relative maxes and mins is basically step 5 of the process. So it's sort of like you can't find the maxes and mins until after you've found those open intervals. So I've got 2 examples for us in this video that I hope are going to make this a bit more clear. So we'll get to those now. So the first example here, I want us to think about this function x cubed minus 3x plus 6. I want us to find all of the relative extrema and the open intervals at which the function is increasing or decreasing. So hopefully you recall from the previous lesson that the first step is for us to find critical numbers. I always find critical numbers by taking the derivative and looking at where that is 0 or undefined. So I'll take the derivative. That derivative is 3x squared minus 3. First, I'll note that this is not undefined for any x. Realistically, you're going to find those where a denominator is equal to 0. This doesn't even have a denominator. So all I really need to do is set this equal to 0. Very, very commonly, these are going to turn into factoring problems. So don't be surprised to see that. This is, I made this one nice for us, I think. There we go. So my critical numbers, if I set these pieces equal to 0, critical numbers are negative 1 and 1. Right? If I had found anything over here, I would include it as well, but I didn't, so it doesn't matter. Right? So I've got my critical numbers. Hopefully now you recall what the second step was. The second step was where we set up intervals for these things. Now, our problem didn't mention anything about an interval, so I'm going to go with the sort of the catch-all interval that goes from negative infinity to positive infinity. And what I need to do is I need to break that interval up using these numbers. And as I mentioned in the previous video, almost imagine you've got this continuum of numbers going from negative infinity to infinity, and then you're going to go through and plop down your negative 1 and 1. And so you can see here that you're going to have 3 intervals. Right? And note, when the question asked, hey, find the open intervals of increase and decrease, these are going to be those intervals. We just need to figure out what each one of them is. Right? So the way that I've always done this is that you sort of write them down individually. The first one goes from negative infinity to negative 1. The next goes from negative 1 to 1, and the last goes from 1 to infinity. With the idea being that you're going to do a little bit of work on each one of these intervals. Right? So now step 3 was where we actually go through and do that work. So let's see here. What that means is we take a number from each interval. And you can't choose either one of these endpoints, you've got to choose something in between. So for instance here, I'm going to do f prime of negative 2. Right? And I've mentioned before, it's often nice to plug into the factored version of this thing. You can pick any version of this derivative up here that you want. Like I said, I'm going to sort of go with this factored version. So this is going to give me 3 times, when I plug in negative 2 to this first thing, I'm going to get negative 1. When I plug in negative 2 to the other one, I'll get negative 3. This is clearly a positive. Right? And so what does it mean if the derivative is positive? It means the function is increasing on this interval. And so you'll notice I've actually already started to answer the question. I can now say that this function is increasing on this interval. Right, so now we move on to the next one. I want to know what f prime of 0 is. Well, if I, again, plug into these things up here, plugging 0 in here and plugging in 0 here is going to get me 3 times 1 times negative 1. That means my derivative, f prime of 0, is negative. And if you want to, you can actually calculate fully out, oh yeah, it's negative 3. It doesn't matter how negative it is, it just matters that it's negative. Because that lets me make the statement that the function is decreasing on this interval, right? So it's decreasing on that interval. And we'll go on and quickly check the last one. F prime of 2 is going to be 3 times 1. This tells me the derivative is positive, and that means the original function is increasing. Right? So again, increasing on this interval. And I haven't formally written that yet, but yay, we actually answered half of the question. The question asked us to find relative extrema and regions or intervals on which the function was increasing or decreasing. We've answered the second part of that question. It is increasing on this interval and this interval. It is decreasing on this interval. Right? So I think that was sort of a combination of steps 3 and 4. Step 5, I think, is where we sort of we look at each one of the critical numbers, right? So what happens at this critical number here? What can you tell me about, what's going on at x equals negative 1, right? The function changed from increasing to decreasing. So this is a potential maximum. Right? How do we find out if it's actually a maximum or not? Well, to do that, we have to plug back into the original function to find out whether or not there was a point there, right? So my original function was f of x is, let's see here, I believe it was x cubed minus 3x plus, I'll have to scroll up to take a look at it, plus 6, okay. So if I plug negative 1 into that, f of negative 1 is negative 1 plus 3 plus 6. That's 8. Yay. So this function has a maximum at negative 1 comma 8. If this had been undefined, it means there's no point, which means there can't be a maximum. It means the function probably went up forever, hit an asymptote, and then started to decrease. That's what that means. Now we can go over here and look. We're decreasing here, then we changed to increasing. So at x equals 1, we might have a minimum. Right, we can find out by plugging 1 into the original function. You'd have 1 minus 3 plus 6. That gives me 4. Great, since that was defined, I know that I have a minimum at the point 1 comma 4. And at this point, we've effectively answered the question. Right? We found the intervals on which the function was increasing and the intervals on which the function was decreasing, and we found all relative extrema. And that's kind of it. I mean, like that's it. That's the first derivative test. That's how it's going to work every single time. I've got one more example for us that's got a little bit more weird stuff going on in it, so we'll take a look at that one next. Alright, so same instructions. I want us to find the relative extrema and the open intervals where the function is increasing or decreasing, and this time I've got a rational expression, and I'm giving us an interval to work with. Rather than saying, oh, go from negative infinity to infinity, I only want us to look at this interval. right? So we'll start looking at the first step. Our first step is supposed to be finding critical numbers, so we'll begin with the derivative of this thing. It's supposed to be low d high minus high d low, square the bottom, and away we go. We'll take, I'll keep simplifying. Distributing here, the numerator of this thing is 2x cubed minus 8x, and that front thing looks like a negative, sorry. This is positive 2x cubed minus 8x minus 2x cubed all over x squared minus 4 squared. The numerator simplifies further because these two things are opposites of one another. Negative 8x over x squared minus 4 squared. Right? Is this thing undefined anywhere? Well, it is. It's undefined whenever the bottom is 0. It's undefined whenever x squared minus 4 is equal to 0. In other words, it's undefined for x equals 2 and x equals negative 2. Right? Is it ever 0? Well, sure. It's 0 whenever the numerator is 0, which happens precisely when x is 0. So I have critical numbers at 0, at 2, and at negative 2. So what I need to do is I need to take my interval, and this is now moving into step 2. I take my interval, which went from negative 1 to infinity, and I break it apart using these numbers, right? So 0 is about here, 2 is over here, and negative 2 is over here, off my interval, which means it doesn't matter. It means this critical number, sure, it's a critical number, but it's not going to have any bearing on this problem because my problem said go from negative 1 to infinity. Anything that's not on that interval doesn't matter. I'm not going to consider it. Okay. So now that I've done that, I can sort of formally set up my intervals. My intervals here are going to be from negative 1 to 0, from 0 to 2, and finally from 2 to infinity. Right? And then what I'm supposed to do is I'm supposed to pick a number on each one of those intervals and test out my derivative. Right? Keep in mind my derivative, the factored version of it is this thing here. I'm just going to write it a little bit further down so we can see it. Negative 8x over x squared minus 4 squared. Alright. So, and this is where you might start to get scared about things. I need to pick a number in this first interval. I need to pick a number between negative 1 and 0. So I'm forced to choose some number like negative a half. And you start thinking, man, I really don't want to plug a fraction into that thing. Keep in mind, all that really matters is whether the thing is positive or negative. So imagine what happens when you plug negative a half into this thing. There's a numerator and a denominator. What can you tell me about the numerator when you plug in negative a half? It's definitely going to be positive because you've already got negative 8 up there. What about the denominator? The magical thing about the denominator is that it's squared. So it doesn't even matter what's inside the parentheses. Anything squared is going to be positive. So you're going to get a positive number on the bottom. This means that my derivative is positive, and that means that my function is increasing. Right? So again, just like last time, we've just found that the function is going to be increasing on this interval. Right? What I'd recommend you do now is pause the video, do the same thing for the next two intervals. I'm going to do it and do that quickly here so you can see it, but let's take a look at that. So f prime of 1, that's negative in the numerator and positive in the denominator. That means my derivative is negative on this interval, which means my function is decreasing. So yay, that means we're decreasing on this interval. And for the last one, I'm going to do f prime of 3. You could have chosen 4 or 5 or 70 if you wanted, but I decided to pick 3, just anything on that interval. This gives me a negative in the numerator and a positive in the denominator. That means my derivative is negative. And so my function is decreasing. Right. So just like on the previous one, my function is decreasing on this interval. Alright, so where do I possibly have maxes or mins? The only places I'm going to have a max or a min is where I go from increasing to decreasing or decreasing to increasing. Here I'm going from increasing to decreasing, so that means I might have a max here. And the way I find out is by plugging in and finding out what is f of 0. Right? Well, my original function, my f of x, was x squared over x squared minus 4. When I plug in 0, f of 0 is 0 over negative 4, which is 0. Great. There's a point there, which means I have a maximum at 0, comma 0. Okay? Over here, my function changes from decreasing to decreasing again, which means I don't have a max, and I also don't have a min. What I might have is I might have a saddle point. I might. Notice it's called a saddle point. It's only going to be a saddle point if there's actually a point there. Right, so how do I find out if there's a point there? Well, the critical number I was looking at here was 2. And so what I need to do is I need to evaluate what is f of 2. Well, if I plug that in, I'll have 4 on top, 0 on the bottom. That means we are undefined here, which means it's not a saddle point either. This thing was probably an asymptote. Right, so I have an asymptote at x equals 2. And you might argue, hey, the problem didn't ask me to find those things. True, I'm just giving you the full picture of the thing, right? So we found that this thing had a maximum. That was a part of the answer. And we found that it was increasing on this interval and decreasing on both of the other intervals. That's all for this example. This, again, was a long video because the first derivative test is a long test. So I hope that makes a little bit more sense. I hope you guys are a little bit better prepared for the homework tonight. The second and final video in tonight's lesson sequence is going to be about some stranger problems associated with this. So I hope I'll see you in that one.